All right, good evening and welcome to lecture number 24 for MT225. This is, I think, our next to last official lecture. We'll be doing some review next week, but for the most part, tonight and Wednesday night, pretty much the last new content that we'll be taking a look at for the semester. So last week, we took a look at stress and strain, both in the normal case, when we apply tension or compression, and in the shear case, when we're trying to cut across something. Tonight, we're going to take a closer look at strength of materials and learn how to look at the properties of a particular material and determine whether or not it's going to be suitable in a particular size and shape to a load. Essentially what we're going to be doing is a little bit on design, and so we'll learn some of the features and factors that we have to take into account when designing, choosing materials to handle a load. So a few administrative points before we get too far in here. Homework 9 is on stress and strain, both normal and shear, and that is due on Wednesday night. I made a bit of a mistake. I think I said it right in the class, but I had it labeled incorrectly in the homework assignment and in the notes. The homework is due on Wednesday 4/28, not Wednesday 5/5. That's next Wednesday, and we will have another homework assignment that's due that night. That night's homework assignment will be a bonus assignment because that is going to be on the same night as we're having our third exam. So I suppose I should have put that in the list of administrivia here. We have exam number 3 coming up on Wednesday, May 5th. Same setup as the previous exams, and although strictly speaking, you're allowed to have 3 uh, index cards, you probably won't need them, but there's not anything on this exam except for strength of materials, stress, and strain. So good opportunity to boost up your grade or get a bit of an improvement from previous exams if you didn't do so well on those. So next week I'll be posting later this week. I'll be posting a sample homework or sample exam 3 to take a look at. We do have our final quiz next Monday night. So May 1st, it'll be based on homework 9. So you can expect to have to calculate some stresses or strains or elongations based on material properties that are given to you. So that'll be our last quiz, May 1st. So I'd ask for homework questions, but there's nobody online right now. So if you have any homework questions and you're watching this later, feel free to text, and I'll be glad to try to answer those questions. But this material is relatively straightforward, so I'm not too concerned about it. So tonight we're taking a look at the strength of materials. So we're going to learn about what the critical properties are that are documented for each of the different materials out there, and I'll introduce you to some of the different resources that you can use to find material properties. We'll talk a little bit about safety factor, which is something we use in design to make sure that our loads never really get to a point where they're much of a challenge to the material. We never want to build a structure that is on the edge of failing under normal circumstances. Safety factor is a way to build in some protection to abnormal situations. For example, if we're designing a tank that is a pressure tank, not a military tank, but a pressure tank, say a propane tank or something like that, we might design it to handle a normal pressure in that tank. But what if an abnormal situation happens, like a fire, and the pressure in that tank goes well above what the expected pressure would be? We'd expect there to be some safety built in so that the tank won't explode unless the pressures get much higher than what we'd ever expect. So safety factor is a way to take into account in a reasonable way and in a mathematical way a little bit of extra protection, essentially over design. So we'll see how that works. And we'll run through a few examples of doing some design with materials, both in the tensile or compressive sense and the shear sense. So we've got a good bit to take a look at. So first, let's take a look at materials in tension. About the only way we really know about the strength of materials is to figure it out experimentally. We don't have a good enough material theory just yet to be able to come up with a model, plug in numbers into the equations, and predict with a significant degree of accuracy at what loads or what forces a particular component will break. We just don't have a good enough understanding of what's going on at the molecular level. We don't have a good enough model for that yet. So we get around it by testing. We take samples of materials, and we take lots of samples, and we pull on them till they break. And we measure what the stresses are, and we figure out where those critical points are in the system, what loads make the material stretch out permanently or what cause it to break. And we do this for hundreds and hundreds of different samples, and we average the results. So we get an experimental measurement of strength. And that's what we'll look at first here, the strengths in tension. So the way that a material deforms when we put it under load does depend on the type of material, and we determine the behavior of a particular material. So whether we're dealing with different steel alloys or different aluminum alloys, different heat treat levels, oil hardening versus air hardening steel, cold rolled steel, structural steel, 6061 T6 versus annealed, all the different types of materials, we can determine what their behaviors look like by performing a tensile test. So a tensile test is an experimental procedure where we grab hold of the ends of a sample of material and we pull on it till it breaks. Now, we learned last time that stress is a material property, that we learn about the stress by taking the force and dividing it by the cross-sectional area of the component. And that's exactly what we do with the materials. We come up with a stress. So we turn the force into an internal stress, and we look at what those stresses are when the material goes through particular changes. So in a tensile test, we put the material in a load frame and we pull on it, and we record how much force is applied and how much deformation occurs. Now, deformation, elongation, is related to the material property of strain. So we have material properties, stress and strain. And in the old style machines, in the old load frames, they would actually have a pen on a piece of paper, and as the load frame applied force, it would move the pen up for the amount of force that was being produced, and it would move it to the right for the amount of elongation, and it would produce a plot. That plot, or stress strain relationship, shows us how stress and strain are connected together. Now, we know that there is a connection between stress and strain. When we apply a stress to something, it tends to stretch out. Think about the slinky applying a force to it, or a spring applying a force to it, it elongates. That was essentially what Hooke's law says. But this goes beyond Hooke's law. We're going to see here that Hooke's law has a limit. We call it the elastic limit or the proportional limit. And that limit, if we go beyond that stress, the material no longer behaves consistently with Hooke's law. So here's a picture of the setup. We've got on the left the load frame, and today, of course, we do everything by computer. We measure the stress and we measure the strain by computer. On the right is a little bit of a close-up of the test specimen and this little clip-on device right here that measures the elongation. We call this an extensometer. It measures the extension of the material. The test specimen's been narrowed down here, so the stress will max out in this narrow region. We want it to break in the narrow region. We don't want it to break up here, so we provide more area, so lower stress. And we run the material through a test. We basically just push a button and the load frame takes it away. And it produces a plot that looks like this. This is a typical stress strain diagram for steel. Not exactly sure what alloy of steel this might represent, but all of the alloys of steel pretty much behave similarly. Now, the point that's marked 0 here is our origin. This is the unstressed piece of material. So in an unstressed piece of material, the elongation or the strain is also going to be 0. So the material sits down here in this lower left corner when it's not stressed. Now, as we start to apply stress, the stress goes up the vertical axis, and strain goes across the horizontal. And what we see here is that we don't see very much strain for the amount of stress we're applying. Now, there's no scale on this, so we really can't tell numbers about it, but as we go up in stress, there's some amount of strain. And this looks like pretty much a straight line. A is our proportional limit. When things are proportional, they behave like a straight line. And most materials behave proportionally as you apply stress to them, as long as that stress doesn't get too high. So point A is our proportional limit. As long as we keep the stress below A, whatever that stress is, how many ever KSI that stress is, the material will always behave in a nice, simple, proportional way. That's useful for design. That's useful to know that when we apply a force to the material, it's going to stretch out a little bit. If we apply a little more force, we get a little more stretch. So we have proportionality between the stress and the strain. That's a nice, simple behavior. But if we exceed the stress at A, that proportional limit, we end up seeing a lot more strain. Suddenly, without very much increase in stress, we get a lot more strain. It seems to almost let go a little bit internally, and the material stretches out a little more easily. That's the point B here is what we call the elastic limit. When a material has elasticity, it means that when you let go of it, when you let go of the force that's applying to it, it shrinks back to its original size and shape. It doesn't permanently deform. Think about what you did in sheet metal. When you bend a piece of sheet metal, you are purposely exceeding the elastic limit. If you didn't go past the elastic limit when you let go of the brake, the piece of sheet metal would just flap back to a flat piece. Think about a spring or a slinky. If I move the slinky a little bit, it goes back to its original shape. It doesn't permanently deform. But if I pull on it too hard, sooner or later it doesn't go back to its original shape. Or think about elastic waistbands and things like that. If you pull on them too hard, they don't tend to go back to their original shape. You have exceeded the elastic limit. Now, in some cases, we purposely want to exceed the elastic limit when we're bending or shaping things, but in other cases, we don't. If this was an airplane wing, for example, we certainly wouldn't want to go past the elastic limit because that would permanently change the shape of the wing. Now, if we keep on applying stress past point B, past the elastic limit, we start climbing up this long hill, and we get a lot more strain, much more strain than we'd ever see below the proportional limit. We get much more strain. So it starts to strain very, very easily, but it takes more and more stress to do it until we reach point C. Point C is the ultimate stress. Point C is the maximum amount of stress that the material can handle without breaking. Now, sometimes we use this. In most materials, most structures, we want to be down here. We want to be down below A because we don't like our structures permanently changing shape. In some situations, we accept a permanent change in shape for the benefit of having a much higher stress. Point C here is a good bit higher than point A. So we're able to produce a lot more stress. One place where we use this is in cylinder head bolts. if you've ever done an engine overhaul on certain types of engines, notably Ford engines, they use what are referred to as torque to yield head bolts. Yielding refers to exceeding the elastic limit. So sometimes point B, point B is the elastic limit, also known as the yield point. Well, if we go beyond the elastic limit, we get a much greater clamping force, but we get permanent deformation of the bolt. When we take that bolt out and compare it to one that's never been used, it is visibly longer. And for that reason, it's usually not allowed to reuse that bolt. So these things are only used once. Some propeller bolts on single engine aircraft are the same way. Once you pull those bolts, you have to replace them. And then we get to point D. Point D is downhill a little bit. Essentially, at this point, at point C, the material starts to fail. And as it starts to fail, it becomes easier and easier and easier to stretch out. So the stress actually falls until we reach point D, which is the fracture point or the fracture stress. That's the stress where the material breaks. Now, this is typical of steel. Aluminum tends to behave similarly for the proportional side. The slope of the proportionality, by the way, is Young's modulus. The slope of this line essentially tells us the relationship between stress and strain. That's Young's modulus. The bigger Young's modulus is, the steeper the slope. It's the ratio of stress to strain. But as we go past the elastic limit on aluminum, we don't tend to see this interesting behavior where we have slow climb up to some ultimate stress. Instead, it just tends to basically be a horizontal line. We don't tend to have much additional stress the material can handle past the proportional limit. So with aluminum, we tend to see it stretch under Hooke's law. Once it starts to stretch permanently, it tends to fail. So aluminum has a much simpler behavior than steel does. There's sometimes a little bit of a climb to it, but it tends to not be nearly as dramatic as with steel. So on the next couple of slides here, I've denoted out what the letters mean, and the most important points to look at are the elastic limit and the yield point, which for most materials tend to be very, very close to the proportional limit. So it makes a good critical stress to consider. And then there's the ultimate strength. So point A is the proportional limit, point B is the elastic limit or the yield point, point C is the ultimate strength. That's the maximum amount of stress the material can handle. And the rupture and fracture strength is usually not something we care about. The ones that are bolded here are the ones we care about, and they're usually numbers that are documented for typical materials. So for example, if I go to my reference book here, and I'm just using the textbook that was referenced in our syllabus, if I go over to the back, and this has a limited amount of material information, you can find much more comprehensive sources on material information. In any kind of exam situation, I would give you the material information involved. So here I'm looking at, let's say, A501 steel. That's a structural steel. It's A36 steel, which, if you have a reference book with you, would tell you exactly what the alloying elements are and the heat treat level and all that. Now, last time we looked at the modulus of elasticity, Young's modulus. That number is documented in this table as 30,000 KSI or 30 MSI. Then there is the yield strength. The yield strength is 36 KSI. So that means I can stress A36 steel up to the point where it carries 36 KSI and it will not permanently elongate. It won't stretch out. When I release that 36 KSI, it will shrink back to exactly its original length. Now the ultimate strength, sometimes called the tensile strength of the material, is the maximum amount of stress it can handle at all. It's past the yield point, so if we expose that material to something near its ultimate strength, it will permanently deform. It will elongate. And the tensile strength for A36 steel is 58 KSI. So I can put about another 22 KSI on that material without it fracturing, without it breaking. So usually the yield strength and the ultimate strength are the two numbers we want to pull out of a table, and those will give us some useful information for design and for checking to make sure we're not overloading materials. We certainly don't want to load structures up to the point where they break, and we most often don't want to load structures up to the point where they yield. Now, for comparison, let me pull up another alloy here. Let's take a look at titanium. Now, titanium has a very high yield strength. It's the highest yield strength in this table at 150 KSI. 150 KSI. I can put 150,000 pounds on a square inch piece of titanium, and it won't even permanently change shape. So 150,000 pounds, that's the gross weight of kind of a medium class aircraft, 727, 737 kind of size. In fact, that's kind of low. That's maybe empty weight of an aircraft like that. So not a lot of, that's a lot of load to put on a square inch of a piece of material. But the ultimate strength is not very much higher, 170 KSI. The ultimate strength is where the material will break. And that's pretty typical of the non-ferrous, the non-steel alloys. Steel alloys, we tend to see a pretty good percentage of the yield strength, of the ultimate strength above the yield strength. The non-ferrous alloys tends to be a fairly small change, like take 6061 T6. The tensile strength, the yield strength on 6061 T6 is 35 KSI. Its ultimate strength is only 38 KSI. So a lot of the non-ferrous alloys tend to have a fairly small difference between their yield strength and their ultimate strength. So those terms are defined here. Proportional limit, that's where Hooke's law works. For the most part, it's the only place where we can really calculate elongation in a reasonable way, because Hooke's law is a nice linear, simple equation that we can use. The elastic limit, or the yield point, that's the stress beyond which we have permanent deformation. And for the most part, that's pretty close to the proportional limit. As long as we're below the elastic limit, we know we're not really stressing the material out to the point of permanent deformation. And then the ultimate strength, the maximum strength the material can handle. We always want to be below that, or we're breaking things. So there's another drawing with those labeled. Point A and B, usually close enough together that we just use B. The ultimate strength isn't really labeled here on this drawing, but it would be right here at the peak. This is another steel type drawing. This is showing, what this is trying to show with point C is that if we let go of the force that we're using to stretch this thing out at point C, it would go back to zero stress, but it wouldn't have zero strain. It would have taken on a permanent set. It would have permanently stretched out by some amount. And exactly how much depends a lot on the material. It doesn't always follow the same slope as the stress does. They just drew that for simplicity here. So here's a nice little table that we might be able to use in things like homework assignments and such. So again, in a in an exam situation, I would give you these quantities. So don't try to write them all down on your reference card. So we have 35 KSI yield strength and 38 KSI ultimate strength. So we can load it up to 35 KSI and it won't even permanently stretch out. That's going to be typically our design limit. We want to design to stay below the yield strength. And if we stay below yield strength, in all cases, we're below the ultimate strength. Titanium, I mentioned that one already. And for good measure, here's magnesium. Magnesium has a 20 KSI yield strength that can hang 20,000 pounds of force on a square inch of magnesium. And it won't permanently stretch out. I'd have to double that load to get it to break. So those are our common strengths of materials. So let's try some examples with normal stress, and we'll try some basic design here. So in doing a truss analysis, we maybe figured out that we've got a member that is going to carry a load of 20 kips. And we need to know, if I'm going to make this out of 6061 T6, how much area do I need? What cross-sectional area do I need in order to make sure that the stress is not, that the material is not going to yield? So let's summarize what the information is that we have here. We have a load. So let me draw a picture and I'll switch over to the camera in a second here. So here I've got a beam that is loaded in tension with 20 kips. And I want to know what cross-sectional area I'm going to need if this is 6061 T6. So let's go over to the display here. So there we go. We've got 6061 T6 with a stress or a force of 20 kips. Now the critical equation to keep in mind here for dealing with stresses and areas is the definition of normal stress. Normal stress is force spread out over an area. And we're being told we want to use 6061 T6. And according to our table, 6061 T6 had a yield stress of 38 KSI, 35 KSI, and an ultimate strength of 38 KSI. So from our table, 35 KSI and 38 KSI. Now, when we design a structure, we don't want it to go beyond yield. So we're going to use the yield stress here. So in the past, we figured out the stress when we knew the force and we knew the area. Now we're turning that around. We're trying to find the area when we know what stress we're shooting for. And what this will give us is the minimum area. Any area bigger will give us lower stress, since bigger areas yield lower stresses for spread out over a larger area. So how we figure out what the minimum area we'd need to get 35 KSI is we plug in what we know. We want the stress to be 35 KSI. The force is 20 kips. And be careful here, you need consistency between the units. If you've got your stresses in KSI, you got to have your forces in kips. If they said 20,000 pounds instead of 20 kips, you'd have to change your yield stress here to 35,000 PSI, or change your 20,000 pounds to kips. As long as you've got the same prefix on both sides, everything will work out. So if it's PSI, it's got to be pounds. If it's KSI, it's got to be kips. And we divide that by the area. Well, this is an equation we know how to solve. We can just cross multiply. So 20 kips times 30 KSI, that puts us into, if we go and solve this equation, we'll have 20 kips divided by 35 KSI. Now, if you work through the units here, remember that a KSI is a kip per square inch. This will give us square inches up in the numerator, and I'll leave that to you to figure out for yourself. But we've got 20 divided by 35. So if I go to my calculator and do 20 divided by 35, I get 0.5714 square inches. Let me rewrite that so it's not as sloppy. 0.5714 square inches. So a little bit more than half a square inch. Now, it doesn't matter what the profile is. It doesn't matter whether I'm dealing with square tubing or a rectangular tubing, if it's solid rod or if it's bar. Doesn't make any difference what it is, as long as I've got 0.5714 square inches minimum, we will not exceed our yield stress. So that would be how we get our minimum amount of area. Now, reality, we might want more area than that. We might say, well, let's bump that up a little bit so that we're not loading right to the edge of our yield stress, because what happens if there's a gust of wind or someone drives a vehicle onto our bridge that's heavier than what we planned for? We don't want the thing to just permanently change shape. We'd want to design it with a little bit of safety built in. But that's how we'd figure out what the area is. We'd use the definition of stress and use that to figure out how much area, what beam am I going to go select off the rack that has the right area so that I load it up to just to its yield point. Now, we might be constrained by what's actually available commercially. Maybe there isn't a commercially available piece of material that has that exact cross-sectional area. So we might have to go up to something that is commercially available. So we could figure out, for example, if this is circular, we could ask, well, if this is pi r squared, what would be the radius? So we could go through and figure that out. 5714, we divide it by pi, take the square root, multiply it by 2 to get diameter. This would be about 7/8 of an inch diameter. Well, maybe 7/8 inch diameter rod is not really easily available, but I can get 1 inch. 1 inch definitely work for us. I certainly wouldn't want to go down in area, but I'd want to go up. So as far as picking materials off the shelf to use, as long as it has the minimum amount of area, we won't be exceeding our yield stress. Now, oops. Let's see what else we have here. So let's try a different material here. Let's say we've got 10 square inches of 5052O. So we've got annealed 5052. And we want to know what load can this handle without breaking. So this is looking at what the maximum force is the material can handle. We're looking at using our ultimate stress. So we go to our reference table and find our properties of materials. And let's see. There we go. So for 5052O, let's do that. So 5052O, and that's letter O, not number O. For those of you who may not remember your material designations, aluminum, non-heat treatable alloy, but it is annealed. According to the great reference library of Google, the ultimate strength is 33 KSI for 5052O. So our ultimate strength, the maximum stress we can have, is 33 KSI. So again, go to the definition of stress, of normal stress. Stress is force over area, and plug in what we've got. We have an ultimate stress. That ultimate stress is 33 KSI. We want to find out what force do we need to apply to 10 square inches of cross-sectional area to get 33 KSI. Well, we can solve that pretty easily by cross multiplying, and our force would be 330 kips. A kip per square inch times square inches, that's kips. So 330 kips, 330,000 pounds is what we can put on 10 square inches of 50-50-2-0. Now 10 square inches is a lot. 5-inch by 2-inch beam, for example, that's pretty significant. A pretty significant amount of material. We can hang 330,000 pounds on that. It'll stretch out because we're beyond the yield point, but it won't break. It'll be just on the edge of breaking. So that's how we can use some of this information. If we know the limits, the yield point, and the ultimate stress, we can figure out things like forces and areas to get those stresses. And that tells us what properties our material has to have, the candidate material that we're using for whatever structure we're dealing with has to have. So let's try another one here. So what load can this support without yielding? Same thing, 50-50-2-0. So we'd need the yield stress for 50-50-2-0, and the yield stress for 50-50-2-0 is 28 KSI. So let's try that one out. So we still have 10 square inches, but now we want a lower stress, the yield stress. So instead of 33 KSI, we're still going to use the same equation. Stress is force over area, normal stress. 28 KSI is the yield stress. Well, that's force over area. We know the area is 10 square inches. If we cross multiply, force is 280 kips. Now, the follow-up question that's asked is, how much will this stretch out? What will its strain be, essentially? Well, to figure out the strain, we have to go back to some of the material from last week. Strain is stress divided by the Young's modulus. So we know how much stress we're generating here, 28 KSI. We need to know the Young's modulus. So we'd have to get the Young's modulus for 50-52 aluminum. And for 50-52 aluminum, in KSI, it's 10,050 KSI. So this is right at the yield point. This is as stretched out as it can get without permanently stretching out. Well, if we divide that through, we've got 28 divided by 10,050. Each inch is going to stretch out. Each inch is going to stretch out by 0.0028 inches per inch. So a little bit more than 2 thousandths, a little less than 3 thousandths of an inch per inch. So each inch will grow by about 3 thousandths. So if this thing's 100 inches long, we're going to see about a 1/4 inch of growth. A little bit more. That's not bad for 280,000 pounds. Again, you're talking airliner weights, things like that. In terms of 18-wheelers, typical 18-wheelers about 40,000 pounds. So you're looking at like 7 18-wheelers, 7 loaded tractor trailers. So that's not too bad. 1/4 inch of stretch. It's looking like some pretty good material. So in order to figure out the physical length that it would stretch, we'd need to know the actual length, but we can certainly find the strain just knowing the stress and the Young's modulus, the relationship between stress and strain. And it's valid to use Young's modulus because we're below or at the yield point. If we were too far beyond the yield point, we really wouldn't be able to use that calculation. It wouldn't be modeled anymore by a nice linear equation. So only when we're below yield and, strictly speaking, below the proportional limit can we actually use Young's modulus to figure out strain. But we'll assume we're below the proportional limit there. So that's tensile strength. That's designing with tensile strength. It's just using, for the most part, the stress equation to make sure your stresses stay below yield. And as long as your stresses stay below yield, you can figure out strains by using Young's modulus. Now, what about shear? Working with aircraft, we spend a lot of time dealing with shear stress because rivets handle shear stress. And one of the problems that we went over last week was figuring out, well, how much stress can a certain group of rivets handle? Well, we're turning that around this week. We're going to see, given a certain amount of load, how many rivets do we need to support that load without shearing? Now, shearing, like we saw last week, doesn't really have a strain to it. So we don't have an equivalent to yield. We only have ultimate strength. So we only typically care about ultimate strength when talking about shear. So the shear strength is typically an ultimate strength. And that shear strength is determined by a shear test, similar to a load frame test, a tensile test. We set up a joint and we pull to load the material under test in shear until it breaks. And then we record what force it broke at, what its original area was, and we figure out what the stress must have been. So we apply load until the material shears through, and it shears through at an ultimate strength. So there is an ultimate strength in tension, and there is an ultimate strength in shear. And the two numbers are not necessarily related to each other. There is kind of a tie between tension and shear. It's beyond the scope of this class. But for our purposes, it's just two different pieces of data in the table. For example, for aluminum 6061 T6, the tensile strength, the ultimate strength in tension, is 38 KSI. In shear, it's only 27 KSI. For titanium, in tension, 170 KSI. Ultimate. Shear strength is 100 KSI. So there's less, in this case, there's less shear stress. And for all the numbers, all the values in the table, the shear stress is, cast iron actually has a higher shear stress than it has tensile stress. Cast iron's only got a tensile stress of 20 KSI, while it's got a 32 KSI shear strength. So it's harder to shear through cast iron than it is to break it in tension. So we have no yield strength to worry about. It's always an ultimate strength. So let's try a couple examples with shear strength. So let's take our favorite rivets. MS-2470 AD4-whatevers. AD4 rivets. For those of you who've been through sheet metal, you've driven hundreds of these. So these are your typical protruding head, universal head rivets. AD, got to know your alloy codes for the FAA written exam. You don't here, but AD you should remember is 2117 aluminum. And remember the nut dash numbers. The first 4 means diameter in 32nds of an inch. The second 4 is the length in 16ths of an inch. So here we have, for this alloy, for 2117 aluminum, the shear strength is 26 KSI. That's how much we can handle per square inch. So if I had a square inch area rivet, I could put 26,000 kips, or 26,000 pounds, 26 kips in shear, and it wouldn't break through. These are 1/8 inch diameter rivets. That's the 84. Well, let's design a joint. Let's say we've got a lap joint, and we want that lap joint to handle a load of 10 kips. And we want to put this lap joint right on the edge of tearing out, right on the edge of shearing through. So let's see how that would work. So we've got this lap joint and we're pulling on it with 10 kips of force. So we've got an upper sheet and a lower sheet, something like that. And we're going to put a bunch of rivets through. Now, those of you who've been through sheet metal know a thing or two about edge distance and or minimum edge distance and pitch and transverse pitch and all of that. As long as we're assuming that we are above those values, so our rivets are not too close together and our rivets are far enough away from the edge that we don't have to worry about those values. Now, the reality of those numbers of your pitch and transverse pitch, or minimum transverse pitch, your minimum edge distance, when you get below those numbers, what you really do is you're making the rivets interact with each other. You're making it so that their areas don't necessarily add up entirely. As long as the rivets are far enough apart and far enough away from the edges, we can count each rivet as acting individually. So it makes it easy to total up the area. When you put them too close together, you get stress concentrations and you raise the likelihood that the base material, the aluminum, is going to break before the rivet shears through. So we want to find out how many rivets with an ultimate stress, with a shear strength of 28 KSI, 26 KSI. How many rivets are we going to need? How many 1/8 inch diameter rivets are we going to need? So we're using MS-2470 84 rivets. That's 1/8 inch diameter. How many of those are we going to need before we exceed the shear strength? So to figure it out, we just use the definition of shear strength. Shear strength is the applied force spread out over the area resisting that shear load. So if we want to put the material, this 2117 aluminum set of rivets, we want to put that material just on the edge of shear, our shear strength needs to be 26 KSI. The force we want to carry is 10 kips. So we can figure out the area that we need for our rivets, the total area that the rivets need to add up to. Well, this is just like the first example problem we did. We can find out the area by cross multiplying and solving, and that'll give us 10 kips divided by 26 KSI. So if we take 10 kips and divide it by 26 KSI, we get a total area of 0.3846 square inches. So 0.3846 square inches. That's how much area we need. But the question asked, how many rivets do we need? So we need to figure out the area of one rivet. Well, be careful here. You got to know how to take the area of a circle. These are circular rivets. It's pi r squared. So it's pi times the radius squared. These are 1/8 inch diameter rivets. So we have 1/16 squared. So if we take 1/16 and square it and multiply it by pi, each rivet, and you've all seen 1/8 inch diameter rivets, you've seen 84 rivets, they're pretty tiny. Number 30 drill bit, 1/8 inch, roughly an 1/8 inch drill bit to drill for those, 0.01227 square inches. So pretty small amount of area there for each rivet. To figure out how many rivets we need, we divide the number of rivets is going to be the total area we need divided by the area of one rivet. So we'd take 0.3846 and divide it by 0.01227. You've really got to be careful of round off error here. Small amount of round off error here could throw everything way off. So I'm keeping the number of sig figs consistent, and I'm expecting I'm going to get an answer that I'll be happy with to 2 sig figs. Well, if we divide that out, 0.01227, I get 31.34 rivets. Now I'm going to have a hard time finding a 0.34 rivet in the bin. And since this is the minimum area we need to get to our maximum stress, we want more area. We want to be underneath that ultimate strength, that shear strength. So we would not say 31.34, we'd say 32. Going up to 32 is safe because it gives us a little more area, which brings our stress down a little bit below our shear strength. And you could go back and rework it and say, well, if I have 32 rivets with 0.01227 square inches, and I'm holding 10 kips, 10 divided by that total area will give you a stress, and that stress will be just a little bit below 26 KSI. So that's how we handle shear problems, especially rivet problems. We look at the area that's involved, or we figure out the area we need so we don't overstress and shear through the material. And then we figure out how many rivets we'd need. Now, you've done this calculation in sheet metal, except you used a table. You went to the 4313 and you figured out for each inch of width in my lap joint, how many rivets did I need? And then you could calculate out how many rivets to use, and that would lay out, you'd figure out your layout from there. Here we're looking at it from a strength point of view, and this is what we do without the 4313, relying just on the materials involved. Now, what if we go to a different area? Well, 5/16 rivets are a little bit bigger than -4s. So are 3/8, so are 1/2s. They're all bigger. Each rivet contributes more area. So we could figure out, we could change the problem and say, well, what if we want to use, let's pick just one of them, 3/8 inch. Well, I know the area I need. I need 0.3846 square inches. What'll change is the area that one rivet contributes to that. So if I'm using 3/8 inch rivets, that's 3/8 diameter, so 3/16 radius. So we figure out the area of one rivet. Area of one 3/8 inch rivet is not 0.01227, it's 0.1104 square inches. Let's double check that here. Yep. Well, if I need 0.3846, I'd still divide, and I get 3.48. So I'd round that up to 4. 4 3/8 inch diameter rivets will do the same job as 32 1/8 inch diameter rivets. So, but 3/8 is a heck of a lot bigger rivet. So that's the basic idea behind those rivet calculations. And I'll leave the other exercises to you for practice. So we've got the basic tools. We know what our stress limits are when we're in tension. We've got our yield stress as our limit. When we are shearing, our ultimate shear strength is our limit. We don't worry too much about compression because compression doesn't really have an ultimate strength or even a yield strength. Things don't yield in compression. Instead, they fail by buckling, and buckling is beyond the scope of our class. So we're only going to worry about things in tension or in shear. So we've got those basic tools. You use the definitions: tensile strength or normal stress, force over area; shear stress, force over area. In practical design, we want to build in some safety. We don't want to load our structures up to their critical limits, because if something unexpected happens or something's a little heavier than it's supposed to be, we encounter conditions that are more severe than we expected, we don't want our structures to immediately fail or immediately change shape. This is what safety factor is intended to do. Safety factor is a way of adjusting the material strength or adjusting the loads that we use. It works both ways to figure out what our maximum, what our minimum sizes should be for material, or what our maximum load should be. We use those critical strength stresses, ultimate stress or yield stress. But in practice, we could leave very little margin for error or for unexpected situations. When we apply a safety factor, we are trying to ensure that the systems we build can handle some amount of load over their designed ratings. Now, those amount of load that we can handle over the designed rating is not something that people are usually allowed to take advantage of. For example, in loading an airplane, typically the wings are designed to handle 50% more load than what they state is the maximum gross weight of the airplane. Just because we can handle that load doesn't mean that we get to legally load the airplane up to that level. In many cases, the safety factors remain the private knowledge of the engineer doing the design. But in other cases, they're public information, but you're not supposed to use that. So when we have a bridge that's rated for 10,000 pounds, it can probably handle more than that, and even by code may be required to handle more than that, but we're not allowed to leave. It's still illegal, and you'll get an overweight ticket for putting a vehicle that's over 10,000 pounds over that bridge. So we build in this safety factor to make sure these systems don't fail and we have some margin for error. It also helps to make these structures have a higher longevity, because as structures age out there, a lot of metal structures corrode, and corrosion reduces the ultimate strengths. It reduces the areas that we're working with, and so it buys us some time for there to be damage or some leeway for them to be damaged or corroded and still be able to handle the loads that we rate them for. So safety factors all around are a good thing, and we want the safety factors, all else being equal, we'd want the safety factors to be as high as possible. But what safety factors do is they cause us to build things bigger than they have to be. We'd use larger areas or more rivets than we really need. And in systems that are sensitive to weight or sensitive to cost, and what engineering system out there isn't sensitive to cost today, we don't want to overbuild things. We don't want to go too far. So there's a lot of art to picking the right safety factor. A lot of times we have it easy because it's specified for us, but in other cases we have to decide what's appropriate and not overkill for the situation. So in using a safety factor, we can apply it and integrate it into the system in one of two ways. We can either increase our anticipated load on paper. We know we're going to rate it for 10,000 pounds, but we design it as if it's rated for 15,000 pounds. That would be applying a 50% or a 1.5 safety factor. Maybe we design it for twice the load, a 200% safety factor, or a 100% safety factor, 200% increase, or doubling a safety factor of 2. So we design it for 10,000 pounds, but we tell everyone it's only rated for 10,000 pounds. We either do that or we derate the materials by the same factor. We don't do both at the same time. We do one or the other. We either make the loads bigger and design it using the real values for the material, or we use the real loads, but we derate the material. We say, for example, I'm going to make this out of titanium. Titanium's got a yield strength of 150 KSI, but I want it twice as strong as it really needs to be. So I'm going to pretend like titanium only has a 75 KSI, half the yield strength. That would also give me a safety factor of 2. Now, in either case, we keep the structural stresses below critical values, and that improves safety, gives us margin. Now, a lot of times in public works, safety factor is specified by law. So when you go out to build a bridge, if a company bids on building a bridge, there is a particular safety factor that can be looked up in the code. So building codes, bridges, buildings, etc., they're part of building codes, the appropriate building code for whatever is being built. We even have this in houses, in residential construction. We have the residential code, we have the international building code, and there are various safety factors built in there. They're not always obvious, because a lot of times they build into things like building code. They just tell you you need to span a certain width. Here's the minimum size 2x lumber you can use, made out of southern yellow pine. You have that builds in a safety factor because they know roughly what the strength of that material is going to be, and they figure out here's what you're going to need to span those walls, or to build a roof truss, or to build a header. In aviation, a lot of times the safety factors are specified as part of the airworthiness standards. Part 23 or Part 25 says that the strengths of certain things have to meet certain safety factors. It's pretty typical in commercial aircraft to rate the wings to 50% higher than the expected max gross weight of the aircraft, 150% of the design load of the max gross weight. That's a reasonable value, and you might say, well, why not make it bigger? Well, that costs a lot of weight. So we try not to go overboard, especially in airplanes. If we are designing a tank, for example, a propane tank, typically a safety factor of 2 minimum is what we'd use for systems that are on the ground. But if that's a system that's going to fly or go into space, we generally back that off to about a 1.5 to maybe even down to 1.2 as our safety factor. 20% safety factor is sometimes used for things that are really weight critical. So safety factor can be applied to either the ultimate strength or the yield strength. It depends on what our limit is. Typically in most structures, we're concerned about yield, so we keep it below the yield point by some amount of safety factor. And that leads us basically to the idea of design. The typical process for design is we do some sort of analysis to figure out what our loads are going to be. That's where truss analysis and frame analysis and equilibrium problems and all that stuff we spent the first couple of parts of the course doing. That's the first step in the design process. And we don't really concern ourselves with what materials are involved. We're just basically looking at the physics of Newton's second law and Newton's first law. With that information, though, now we start the design process. We have to pick a material, and sometimes it's wide open. We can pick any material we want. In other cases, we're limited by things like cost and availability. Like right now, if you're building something, certain types of plywood are probably not high on your list for things you want to go buy right now, because the prices have gone insane on things like OSB, oriented strand board. So maybe we look at a different material, something that's got a lower price per foot or price per square foot. So sometimes the material is about availability. Sometimes it's about cost. Sometimes it's about other conditions. Like we're going to be in a high corrosion environment, so we want to pick a material like stainless steel or titanium to maintain that structure rather than less robust materials like magnesium. Once we've got the material, we have to pick a safety factor. And that safety factor is usually going to be told to us if we're building something to code, or we might pick it out of typical design best practices. And then we figure out sizes. With the material, we know the ultimate strengths, whether it's in shear or whether it's in tension. We know the yield strength and tension. With the safety factor, we can figure out what the areas need to be to maximize our stress or minimize the area corrected with whatever safety factor we've applied. And then we have to be careful because we've got to make sure that our deformation isn't too much. Maybe the material we've picked can handle the stress, but it's got such a low Young's modulus that it's going to cause our structure to stretch out too much. Might not go past yield, but it might still be an uncomfortable amount of stretching. So we might need to go back and reevaluate and say, well, we need a stiffer material. Maybe that magnesium with a 6,500 KSI modulus of elasticity just isn't enough, and I've got to go to something a little stiffer that's going to not change shape as much. So this tends to be what we call an iterative process. It's something we end up going around in circles on. We'd say we figure out our stresses, we check deformation, we check our limits, and we find maybe that's not satisfactory. So we go back and we start again. And we adjust from there. So let's try a design example here. Let's say we've got a beam that is loaded up to 5 kips in tension. So we've got 5 kips in tension. And we're going to build a bridge. And we want that bridge to have a safety factor of 2.5. So we're going to make it a really safe bridge. So we want to have a safety factor. We've got a prescribed safety factor of 2.5. So that's 250% above our critical limit. So we've done the analysis and we figured out this member is going to be loaded to 5 kips in tension. And we need to pick a material that's going to handle that load under the given safety factor that we've got. So let's pick a material. Let's go to structural steel. So we'll go to structural steel, and structural steel has a yield strength of 36 KSI. So our yield strength is 36 KSI. That's the maximum amount of stress the material can handle. Now, we did a similar calculation to this at the beginning of the evening, but different loads. With 36 KSI, we can figure out what the area needs to be. Now, that would be a minimum area to get us 36 KSI, but that doesn't bring in the safety factor. And we have a lot of flexibility in how we apply the safety factor. We can apply it after the fact to the area. We could find the minimum area and then multiply it by the safety factor. We could, instead of dealing with 5 kips of force, we deal with 2.5 times that. We go to a higher value. So we could say 12.5 kips, or we could reduce the strength of the material. We could say instead of 36 kips KSI, it only has 14.4 KSI. Either way we do it, we're making life harder for the material on paper. We're treating it as if it's in a harder situation than it actually is, either more force than we anticipate by the amount of the safety factor, or less strength than we anticipate by the amount of the safety factor. Either one will lead to increasing the area by the safety factor. So it's usually pretty easy to apply once you've figured it out. So let's do it as if we're applying it to the load. So we really have a 5 kip load, but I'm going to pretend and I'm going to design this as if the actual load, so the safety factor corrected load, is going to be 12.5 kips. That brings in the 2.5 safety factor. So that's our design load, not our real load. So we're going to get an area out of this calculation that is going to keep this material stressed below its yield point by a good bit, by a significant amount, so that even at the maximum load we expect to encounter, we're never going to be anywhere close to our yield strength. So let's see how it works out. If we do our definition, stress is force over area. We know what we want the stress to be. The stress is 36 KSI. And our force we're pretending is 2.5 times bigger than what we really expected and calculate it to be. So we say 12.5 kips of force divided by the area. So we'd cross multiply and solve that. We'd end up dividing 12.5 by 36. And we get an area of 0.3472 square inches. So that's the area with the safety factor already included. You only have to put the safety factor in once. In fact, you must only put the safety factor in once. If you put it in multiple times, either you'll end up with something that's way oversized, or you'll end up with something that where the safety factors cancel out and you'll be exactly on the critical stress. Now we could go back and say, well, let's find out what the real stress is in the beam if we put 5 kips on it and we actually use this 0.3472 area. And we'll see that we're going to get something that's a good bit smaller than 36 KSI. So let's go off to the side here and just check our load and make sure that that our stress, when we put 5 kips on it, is less than our yield strength. So if we take 5 kips and divide it by 0.3472, we get 14.40 kips per square inch KSI. Now that's a good bit below the yield strength, and that is the maximum load that we expect to put on this. So by using the safety factor to amplify the load, we ended up with an area that will keep the stresses low. And you can try it the other ways around and come up with a way that you like the best. You can just calculate it normally, find the area that will drive the ultimate drive the stress right up to yield, and then multiply that area by 2.5, or cut your strength down by 2.5 and do the analysis. Either way, you should end up with exactly the same results. So that's a little bit on the idea of design. Now we could check our stretch here, how much strain we've got. For that, we'd need to know something about the length. But for steel, we've got a pretty rigid material. We've got 30,000 KSI. So if we needed to figure out our strain would be our stress divided by the Young's modulus. Now the stress that we'd use is going to be the actual stress in the member. It would not be our ultimate stress, because applying the safety factor will keep us from ever really getting to that point unless we severely overload this member. So we'd take that reduced stress, that 14.4 KSI, and divide it by the yield, or divide it by the modulus of elasticity, and that's 30,000 KSI, and we get a pretty tiny number. We get 0.000480. inches per inch. Now, in any kind of regular structure, bridge or something like that, we're not going to be talking more than a few, maybe tens of feet. So not very many inches, tens of feet. If we say 10 feet, that's 120 inches. 120 inches with less than a thousandth of an inch per strain or per inch, we're talking about 50 thousandths, 50 to 60 thousandths, about a 16th of an inch of stretch over 10 feet. That's pretty good. We'd only really have to worry if we were talking about several inches. Just think about what that would do to your analysis. We based the truss analysis on knowing lengths and knowing geometry. If the material moves too much and stretches out too much, then those numbers are all off. And you'd have to go back and redo the analysis with the new numbers. And a lot of times, this is what a computer program would be doing. What we call an iterative solver would go through and see how much stress they got and how much strain they got, recalculate the geometry of the structure, go back and recalculate the loads, and do the whole process over again. And it would keep on going until it reaches a final solution. So that stretch is certainly fine. That strain is not nearly enough to cause a problem. Let's try one with rivets. So let's try a design problem there. Let's say we've got a lap joint. So similar to the previous problem here, same rivets, since we always use AD rivets. Our shear strength. So our shear strength is 26 kips per square inch. And we have this lap joint we want to do. We want that lap joint to carry, let's say, 5 kips. So we'll have the same 5 kips we had from the previous problem. So we've got this lap joint. And we're going to use some number of 1/8 inch rivets. 1/8 inch diameter, 2117 rivets. We want to find out how many rivets we're going to need. But because this is an airplane, we want it to be a little bit stronger than what we expect it to be. So, but not too much stronger, or we'd add way too much weight. So a typical safety factor for everything except the wings on an airplane is typically 1.2. So our safety factor will be a 20% safety factor, 1.2. Now in the last problem, I used the safety factor to amplify the force. In this problem, I'm going to use it to reduce the strength. And we'll get the same kind of answer. We'll end up with more rivets. If we pretend that the rivets are weaker than they actually are, we'll end up putting more rivets in there. And that will lower the overall stress and keep us farther away from that shear strength. So I'm going to correct my shear strength with my safety factor, and I need it to be smaller, so I've got to divide. Don't make the mistake of multiplying it and overemphasizing your strength of material. We either amplify the load or we reduce the strength. We make life harder for the material. We pull on it harder or we make it weaker. So corrected for safety factor, my 26 KSI of shear strength will now be slightly lower. It'll be 21.67 KSI. So let's figure out how many rivets we need. The shear stress is force spread out over the area resisting that force. Well, the shear stress we're shooting for now is our reduced shear stress, 21.67 KSI. We're going to use our regular force, 5 kips. And we need to know the area. So if we cross multiply and solve that, we get an area of 0.2308 square inches. Well, for an 1/8 inch rivet, from our previous drawing, we had 0.01227 square inches per rivet. So therefore, the number of rivets will be 0.2308 divided by 0.01227, and that's 18.8. So we'd go up. We always go up on the number of rivets, so we'd use 19 rivets. Now, if we actually go back and calculate the real stress, we'll find that it's going to be lower than the shear strength. We'll find it's lower than that shear strength, closer to 21.67. It's certainly close to the shear strength, but it's not going to exceed it even if we overload the airplane a little bit. And that may not mean putting more weight on board than what we're supposed to. It might mean we fly in turbulent conditions, or we have unexpected gusts, or maybe the pilot is a little too rough on the controls. All of those kinds of forces could lead to momentary overloads of the structure. We want that structure to be able to handle that slight overload. Can't go too far because it's only a 20% safety factor. And there have been plenty of cases where people have overstressed airplanes. It is not impossible to apply control forces or to handle the aircraft in such a bad way that you end up breaking it. It does happen. So we have to be careful with that. But we're not overly ambitious with our safety factors. We want to keep the loads, we want to keep the weights low. We wouldn't design everything with a safety factor of 2 or 3 or 10 for an airplane because we'd have no room for useful load. All right, so that's design with shear and tension. So major points to recall here, we have our ultimate strength and our yield strength, the relationship between stress and area and force, our area calculations leading to after we select materials, how safety factor works, and finding numbers of rivets in a joint. So those are the examples I'll run. Next time on Wednesday night for our last formal lecture, we will be looking at stress and strain in beams. So we'll go back to the simply supported beam where we have a pinned support and a roller support at the ends, or somewhere in the middle, somewhere in between, and we'll put a load on it, and we'll look at what the stresses and strains look like. Here we're going to be putting together material properties and geometry properties, just like we did for strengths of materials. We can't call a beam that has a load on it other than pure tension or pure compression. We can't really do the same kinds of stress analysis. When we put load on a beam, it tends to bend. And bending is a combination of stress and strain, as we'll see next time. So we'll see about beam deflection. We'll learn about how beams deflect and how much deflection we get. So we'll consider things like diving boards, for example, and how much deflection we get out of those when we put somebody on the end of those. Or we'll look at things like floor joists and how much deflection we get when we put a load right in the middle of that floor joist. And we'll see what some of the regulations are, the codes and such are for handling that, and how we can adjust our design to compensate for it. So we'll take a look at that next time. Have a good evening. I'll see you Wednesday night.